Yes. Okay. Thank you very much, and thank you to all of you for the nice talk, for the nice workshop. Sorry. Exactly, with a lot of white wine. And so I come from the University Paris-Saclay, and I will talk today of this oscillating amorphous solid, and actually it was inspired by a work by Giuseppe and Srikant and Davide Fiocco, which is already, 2013. So what they did is that they perform oscillatory athermal shear on a model, a numerical model with particles which interact with soft potentials, so are soft glasses. And the important thing, compared, for example, to the experimental talk that we had on Monday afternoon, is that there are no rejuvenation effects. So, so usually when you shear periodically, you think that it becomes more and more ductile, but here we will see that it's the opposite, okay? And so this is the inspiration. So there was a paper by myself, by Kirsten, by Laurent Talon, who is in FAST, by Ezequiel Ferreira and Eduardo Giagla, who are in Bariloche. But the main actor is Chen Liu, is in the picture, is the guy who really did the job. And so now I will spend a little bit of time on our model. So what we did is to study this protocol using these elastoplastic models that were introduced by Susan, by Kirsten, and by other people during the talk. And here is a continuum version. So let me explain what we did. So in our physical model of Srikant and Giuseppe and Davide, we had particles which were interacting with potential. And so if you want to do the simulation, you have to move all these particles. You deform the system and you look at the new minimum of the energy with the system deformed. In our approach, we follow the idea of Poisson and Cauchy. So the idea is that you would like to describe the solid not like with its granularity, but like a continuum field. So you divide the solid here, everything will be in 2 dimensions. So you divide the solid in squares, and then you start to shear them. So if you have standard elasticity, what you have is that the stress in each square grows linearly with the deformation, with the strain. But what happens in simulation and also in experiments is that in these amorphous materials, which are emulsion, foams, so are soft glasses, what happens is that you observe that there are irreversible rearrangement of particles, which are called shear transformation. And these are point-like deformation in the sense that there are few particles, 5 particles, 4 particles, that rearrange in a way that when you go back, you will not go back to the same position of the particle. So it's not reversible. And you have plasticity in this sense. In this square, where you have the shear transformation, the system becomes like a fluid, and the strain locally grows without the growth of the stress. So the idea that, I start work on that with Mathieu, actually, we just came, is that instead of describing the position of the particles, we will use, in the same spirit of field theory that was described yesterday by Bobo, we will use the local strain, epsilon x. So each point of the space has a given strain, and this strain can fluctuate, it's like a manifold. Okay, so now let's go to the equation. So what we do is, okay, the standard elasticity in 2 dimensions, you can associate to each deformation an elastic energy. And this elastic energy is quadratic in the 3 strain components. And in amorphous system, there are 2 elastic modulus. So epsilon 1 is compression and dilatation, and B is the bulk elastic modulus. And then you have the shear with 2 components of the shear, epsilon 2 and epsilon 3. And so is a quadratic potential. And now, if you want to add the fact that you have this irreversible rearrangement. What you have to do at the local level is that instead of using just the parabolic potential when you apply a deformation, you need to have a potential which is not quadratic. This in general is plasticity, is less than quadratic. But if you now remove the constraint, you will go back to the same minima. So the only way to have irreversibility is that the potential should have many minima in such a way that when you deform, if you are far enough, then you follow in a new minima, and this is what plasticity is. So for me, that I come from disordered system and statistical physics, this potential is a disordered potential. I mean, this is what we use in the model, so it's perfectly quadratic locally. This translates the fact that the solid at the beginning is elastic. But then you have a new parabolic potential, and depending, it can be deep or less deep, and this tells you if the material is going to fail soon or later, if it's deep later. And so what we do is that we select at random the parabola. For each block, so for each value of R, we have a sequence of potential, and this is a problem now, which is, is a problem of disordered systems because you have this stochastic potential. Sorry, epsilon is epsilon 3, because this is a good remark, because so in principle, you have plasticity in the 3 direction, okay? Now, because you shear in this experiment along epsilon 3, is useless to put this, so you have, in principle, many parabola also along epsilon 1 and epsilon 2, but because there are small fluctuations along epsilon 1 and epsilon 2, you keep the perfect quadratic potential, and you put this disordered potential only along epsilon 3, and so now I will call epsilon 3 epsilon because it's the only that remains. And so in order to have now, because I have these 2 other components, and if you do mechanics, you know that they are not independent. So now if you want to write something that depends only on epsilon 3, you have to impose this Saint-Venant constraint. And so if you write, now if you integrate, I mean, you remove epsilon 1, epsilon 2, the price to pay is an interaction among this epsilon 3, and this G is the Eshelby kernel that was already discussed. So it's a kernel that decays like 1 over R power D with this quadrupolar shape. So at the end now, if we forget everything, we have an energy which depends only on one, is scalar, it depends only on one epsilon, on only one component. It is disordered because V is disordered, and it is interacting because of the Saint-Venant constraint that you impose. Okay, so now what we do with this model is that we put a constraint. So there are 2 protocols usually you use. Either you impose a stress, either you impose a deformation. Here we impose a deformation. So we add, so we do the gradient exactly like Srikant and Giuseppe. We look at the minimum. So we do an equation of motion that is the gradient, okay, so that follow in the minimum. But we add a global constraint. So the average value of the strain, epsilon, all the manifold, is equal to gamma, and kappa is a very large constant, okay? Okay, so this is what we do. And if we implement this protocol, we can compute the stress, which is just the derivative of the energy, okay, as a function of the strain that we impose. And we run the simulation of this. So with respect to Kirsten and to Susan, the difference here, this epsilon is a continuum field, okay, it is not discretized. And so what we have is, maybe I use this, is that depending on the preparation, I will explain how we prepare. Depending on the preparation, we have two different kinds of materials. We have materials that yields, like the yellow or the red. So you see that the strain grows monotonically, and then it saturates to a value which is the yield stress for our parameter is this value. And we can say that the strain at which yields is this one, okay? At the beginning is a solid, and then it yields, so we can identify 0.41, the yield strain. There are materials like the violet that are actually brittle, okay? And so what you do when you strain them, nothing happens, and at certain point you have a failure, so there is a catastrophic event with a shear band, and then you saturate to the value of 0.37. Okay, what is the difference between these materials? So what I didn't say, is how I prepare the material. And this depends on essentially the first parabola that I put. So the system at the beginning is prepared in this reference state, as was explaining yesterday, Bulbul. So epsilon is equal to 0 everywhere. And then, so there is no strain. And now everybody is sitting in the minimum of the first parabola. And now you have the freedom to select bigger parabola, deeper parabola, and this will correspond to well annealed, or shallower parabola like this one, which corresponds to poorly annealed. So depending on how you select the initial condition, you control the energy. Yes?
That picture that you have.
Yes.
This is not predefined, is it, in your case?
So what I do is there is an initial condition, and after that you generate the next one using a distribution that is the sum feature. So the depth, I think, is uniformly distributed in some way. Okay. Yes.
Is there a reason to be at the bottom of the first parabola?
You want to minimize the energy.
Okay. You're still always, yeah, okay.
Yeah, every time, so what I discuss are always the minimum, because we are quasi-static, so you always minimize the energy, okay? Yes?
And that reference state has zero stress?
Yes.
Has zero stress and zero strain. Yes. You can do that.
Okay. So now what I want to show is so before I show the strain curve, but now we can measure the energy as a function of the deformation, the energy of the different samples. So these were the ductile sample. So as I say, they are fully annealed. So the temperature, if you want, the energy in which they were prepared is I, okay? And then when you deformate them, they the energy decrease and reach this value, okay, which corresponds to this region. Okay? When they are here, the energy is, in our simulation, is minus 0.122, which is the energy of what I call liquid. I will explain why it's a liquid. And while if I take the one who fails, so here they fails, what you see is the energy increase, but not too much, okay? And now to understand what is going on, so the difference between ductile and fragile is that, so these are the two-dimensional system, and this is an accumulated strain. So what you see is, if you take the yellow case, for example, no, this is the red case, what you see is that when you are here, the strain accumulates homogeneously in the sample. This is the ductile case. You see a little bit of shear band maybe here, but it accumulates homogeneously. So it means that this energy is, is the local energy in all the system. And the situation is very different in the fragile case, because you see that this is the blue case. you see that the strain accumulates only along a very narrow shear band, okay? So here the system is a liquid, while here is the same solid that you had at the beginning, okay? So this is what happens in the uniform shear. And now there is the question is what happens when you vary. So this is fully annealed. This is very well annealed. And so what happens when you vary the annealing? So there are different, it's quite controversial. One big question is, do you see before the failure avalanches that becomes bigger and bigger or not? Okay? And the second big question is, do you have a critical value of the annealing in which, above which you see the failure or not? So it's controversial. There are at least 3 opinions in the room, so I will change the subject. And, and then we go to the periodic case where I think things are more clear. So this is the simulation of string, so it's a later paper. These are still the soft glass simulation. And what you see is the uniform shear are the lines, okay? So this is the ductile, this is the more fragile material. And you see that when you uniform shear 2 different materials, you see different stress strain curve. Now what is sigma max and gamma max? So you have this oscillation of the periodic oscillation. So the amplitude of this oscillation is gamma max. And the frequency is almost 0 and doesn't count. So the only parameter that counts is how far you go in the oscillation. And then you measure the maximal stress during the oscillation. And so what you do is that you have to oscillate these materials many times, reach a stationary state, okay? And then you look at the material you have formed once oscillate, after many oscillations. And what they see is that there is a very well-defined value at which the material fails, no matter what its initial preparation. So you reach a new material that forget what was at the beginning, and in general is quite fragile because it fails, okay, and develop a shear band. It's clear, because this is what I want to show later. Okay, so now we want to implement the same thing using our methods, because then we can do bigger simulation and we can also maybe relate to what happens in the uniform case. And so the key point is that we have to understand what to do when once we leave a parabola and then we come back, what we should do, okay? So there is a big difference between the disorder which is induced by quench impurity. For example, imagine that you do this experiment looking at domain wall, magnetic domain wall that go back and forth. They feel the impurity in the sample and the impurity stays there. So the disorder is quenched, this potential doesn't evolve. But in this case, once you leave the parabola, it means that the particles are rearranged in a reversible way. So when you are coming back, you are not seeing the same parabola, okay? So you have to refresh the parabola. And this is really the key point that we spend a little time to understand. And only if you do this, so only if the disorder changes when you go back, then you have a picture like this one. So these are our simulation. In the line, you see the uniform shear that I discussed before. And then you do many, many oscillations. And big gamma, the gamma max, is the amplitude of this oscillation. And so what you see is that in the case of the ductile case, so the yellow, red, and green, then you have exactly the same material. And you have a phenomenon which is the opposite of what you described. So you have a more fragile material. Because the idea is that during this oscillation, you kill the shallow parabola and you remain with big parabola. And this is what gives you the more fragile material. And now if you start very, very fragile, like the violet case, then you fail you fail later, you fail here. But once you fail, then you reach exactly the same stationary state, which is this mixture between solid and liquid with a shear band. Okay? Yes?
These are the amplitudes of the stress and the strain.
Yes.
What does the instantaneous stress and strain look like? Because once you get above that yield point, I presume that you have an elastic response followed by yielding, followed by elastic, followed by yielding. How does that response change? Because this is the maximum value.
Yes.
What happens instantaneously?
Instantaneously, it happens that you have, as you said, elastic part, yielding part, and then it continues like this.
And so does the yielding remain the same brittle, or does it become ductile, or does the yielding type change?
No, it's always remain fragile. Always you have the shear band. So I will show this later. 1 second.
So I just wanted a clarification on what you mean by fragile, because
There is a shear, there is always, so there is no, I will show, there will always be a very well-defined shear band.
If I understand Simon's question, I think what he plots is always the instantaneous stress and strain. You are in AQS, and in AQS, the stress,
Yes,
if
but
you stop...
inside the period, it's not the max.
Exactly, but if you stop everything, you just stay at that value. So the gamma is the amplitude. But in the AQS, the stress and strain are always instantaneous. There is no time effect.
This is cyclic. So.
Yeah, that's what I...
Yeah, I think I'm agreeing with Alberto. Within the cycle, there will.
what is the question?
So, no, good. Okay, so let's go on. So the one important point I want to make is that now if you do this many oscillation, okay, you can look at the stress, you can look at the energy. And so what you see is that if you take the ductile samples, the energy decrease with the amplitude until this critical point, which is 0.4725. And the energy of all sample is also given, is minus 0.16. So this point is a solid, and it's the last solid you can see with this oscillation, okay? After that, you fail, and then the energy starts to increase. And if you prepare with an unbelievable well preparation, then you fail later, but then you follow again in the same curve, okay? So this is the phase diagram I want to show. So you have a solid liquid transition, okay? And the important point is that when you increase the value of gamma, you forget, especially if you are in the poorly annealed case, you forget your initial preparation and you arrive to a phase which is completely independent of the initial preparation, and all samples fail exactly at the same gamma star, okay, except this very stable one, which fail at the bigger gamma star, and above it, you arrive to a phase that at variance with the uniform shearing is completely dependent on the initial condition. And so the last part is about this phase, so I think is your point. So this phase is a mixed phase, and we have, so this is a picture of the accumulated strain. So you see that this is along one period. You see that the strain, half a period, because otherwise it will be negative. The strain accumulates along this shear band. And if you integrate over y and you look at the energy, you see that this dark part here corresponds to the energy minus 0.16. So the energy of the solid, which is the solid at the transition, and the energy in the shear band is exactly the energy of the liquid that I showed you before. And now if you rescale everything correctly, you get that you have a nice collapse when you assume that the shear band is actually this form. So at gamma star, at the transition, the shear band is already finite. And so this is what we think is the transition is of the first order because you have a jump and you are in, it's not continuous. And so here you have a small jump, and you can describe the energy. The yellow line is given by this analytical formula, which depends only on the parameter, on one parameter A, which is here, and we test it. So what we said is we reach this solid, which is very well annealed, is independent on the initial condition, and then increasing a little bit the amplitude, you create already a finite shear band, okay? And then what you have is completely independent on the preparation. You have a shear band, which is the liquid, and you have the rest, the solid part, which is at this energy E star, okay?
Running out of time, you can say it later, but can you say something about the significance of that gamma y being less than gamma star?
Yes, it means that the transition is a gamma star, okay? And gamma y, which was the one of that I introduced at the beginning, so the yield stress in the uniform case is smaller, and so it means that when this form of the energy is valid starting from gamma star, and so when you have gamma equal gamma star, this is positive, so it means that for gamma smaller than gamma star, the energy is E star, and for gamma bigger than gamma star, the energy is bigger, so you have a jump. This is the meaning, okay? Okay, so I want to spend a few words about how much you have to shear in order to reach this steady state. So what we see is that in the solid phase is quite fast, in the sense that of the order 20, 30 periods, you reach already the energy, and so you are in the steady state. So when you are in the solid phase, you should observe the shear annealing quite well, okay? When you are in the mixed phase, in order to be able to observe really a perfect stationary state, it takes a much more long time. You see here, okay, you have all this plateau here, here, and here. And this is actually interesting, and actually I'm not sure that Shrikant agrees with me, because maybe I show directly. So let me show fast. So let's say if you are in the poorly annealed case, what you have is, so this is the number of oscillation, and this is the position of the shear band. So the shear bands, what the shear bands does is start to diffuse inside of the sample, okay? And then you wait essentially that it diffuse in the full sample, which takes certain time. Now, in the other case, when you have the very well annealed, this is much more interesting, because at the beginning, what you have is that you have to break the solid. So at the beginning, you have the formation of the shear band that grows, okay? And now it doesn't move diffusively, it moves ballistically. It actually invades the black region, which is the very well annealed case, to leave the marginal solids, which is at the energy star. And only when is able to reach all the sample, then it starts to diffuse, okay? And this is depicted in a movie. So let me show. So this is the poorly annealed case. So you have the shear band, and the shear band, during the different oscillation, it moves a little bit back and forth, and it diffuses, okay? Now, if you start from a very fragile, the things, what you should observe is before the shear band grows, reach its size, and then moves ballistically. Let's see. So it grows, move ballistically, always in the same direction. And this is because the solid is too much annealed that it invades. And once there is no broad black, then it starts to diffuse, okay? And this is what we see in our simulation. And actually, we try to understand why, but we were not able to give a clear answer. We have some idea. So to conclude, what we show is that in general, when you do this quasi-static protocol is non-intuitive, but it should shear anneal the sample. From a disorder point of view, it's very clear what is going on. You are removing the shallow parabola, but I think it will be nice to see this in an experiment, that the system becomes more fragile. And at a certain point, you arrive to a solid that you cannot sustain anymore the fact to be solid. So it develops a fracture, it develops a shear band. And then, depending on the initial condition, you have an intriguing transient, because if you are already marginal solid, then it just diffuses. If you are not a marginal solid, then you will see the shear band that before transform the solid in the marginal solid, and then it starts to diffuse. And so, okay, one of the challenges that we had at the beginning was to try to transform the mesoscopic model in order to include this oscillation, and we understood, I think, what should be done, and we find the results which are sound. And now I think one of the big problems, Roberto, it will be nice to see in an experiment if it's true that you have this shear annealing when you slowly oscillate and not fast. Thank you very much.